Hello, I'm Frederick Toombs from the University of Waterloo. I'm presenting my work on Mocarabe, a set of high-performance, time-multiplexed overlays for FPGAs. Thank you to my co-authors and collaborators Ali Reza Malat and Professor Nachiket Kapre for allowing me to present. First, I'll provide an introduction, then delve into the Mocarabe architecture followed by its complementary compiler. I'll cover some results and conclude. Our key contribution is that we've developed a flexible, high-frequency overlay design with a configurable number of communication channels, which runs at 645 to 768 MHz on an Alveo U280 FPGA. We've also developed a compiler that can map C dataflow kernels to our overlay. Our first claim is that Mocarabe provides 1.8 to 3.4 times higher Fmax compared to similar CGRA overlays, while operating with order of magnitudes larger array sizes at 19 by 69 logic blocks. Additionally, our experiments show that Mocarabe can be up to 9.2 times faster than Vivado HLS. There is enormous potential for FPGAs in the data center. Cloud computing providers such as Amazon Web Services and Microsoft Azure offer FPGA instances to the masses. However, FPGA application development in RTL is complex, and more automated and accessible approaches to hardware design are needed. A common approach to simplifying FPGA application development is high-level synthesis, which compiles C or C++ down to RTL. When scaling to an entire FPGA device, our experiments found that HLS suffers from low frequency, up to 9.2 times away from peak Fmax, which we attribute to communication breaking down between computational resources. Coarse-grained reconfigurable architecture overlays are an alternative approach to simplifying FPGA application development. These overlays trade off flexibility for high Fmax and performance guarantees. A compiler is required to manage time-shared resources and to translate C code to a configuration of the overlay. The overlay architecture our research proposes is a 2D array of logic blocks interconnected with a directional torus. Logic blocks consist of a processing element and a network on-chip router. The interconnect is pipelined at each router. Data movement and operation execution is statically scheduled by the Mocarabe compiler. The architecture can have a variable number of parallel communication channels. Seen here is the single channel layout for an n by n array, and here is a 3-channel layout. Each processing element can be configured as an operator, such as a multiplier, which requires DSPs, or an adder, or it can be configured as an I/O. If the PE is an operator, it stores incoming operands into shift registers. When they're scheduled to do so, these operands are then loaded into the ALU, and the operation is executed. The output is then sent to the NOC. The initiation interval II determines the number of contexts, and thus the depth of the context memories. Every II cycles, the schedule is repeated, with new input values. The routing network can have a variable number of parallel physical channels. A router is added to every logic block for every additional channel. A router accepts inputs from the south and west neighbor routers on the same channel, and the local PE's output port, and routers will output to the next north and east routers, and the local PE's input ports. The goal of the compiler is to map dataflow graphs inferred from C functions to an overlay configuration given a target initiation interval. Our current benchmarks consist of feed-forward dataflow kernels. We do not currently support conditional execution or loops. This is what our compiler flow looks like. The first input, the dataflow graph, is composed of nodes, which represent operations, inputs, and outputs, and edges, which represent both values and data dependencies between nodes. The other input is the initiation interval, which determines how often the overlay can accept new inputs. The compiler flow has four phases: operator allocation, DFG partitioning for PE reuse, placement, and scheduling. If the problem is found to be infeasible during scheduling, we increment channel count and restart until a solution is found. First, we allocate just enough PEs to execute all of the dataflow graph's operations with a desired level of resource sharing. We then use an integer linear programming formulation to partition the dataflow graph, which is encoded as a hypergraph. We pack at most II operations of the same type into each PE, keeping every PE as busy as possible. Next, placement maps every packed PE to a specific XY site in the array. Of note is that any PE can be a multiplier. There are enough DSPs to go around. We minimize the total quadratic wire length over the torus with annealing. The core of the compiler is the scheduler, which is formulated as an integer linear programming problem and solved with the Gurobi solver. The scheduler routes every net through the torus over a modulo schedule. The ILP formulation has binary variables, which indicate a net's use of a resource, and there are variables for horizontal and vertical routing, as well as for controlling the PE router interfaces. We encode the netlist as constraints on the routing network enter and exit variables based on every net's source and destination. Every net is scheduled independently, and dependencies are realigned later using the processing element shift registers. Constraints such as routing resource exclusivity ensure that resources are shared without conflict. Everything is modulo scheduled with modulus II, with the objective to minimize routing resource use. Constraints and objective functions are explained more comprehensively in our paper. To help visualize data movement in the array, here's an example. On the left is a small dataflow graph inferred from a C kernel, partitioned with an initiation interval of 2, and every resulting PE placed on the array. On the right is the output of the scheduler, which determines resource ownership along the data's route. Every 2 cycles, a new X value is sent out, followed by a new A value in the next cycle. In this case, both nets use the same channel to get to the same location at x0, y0, one cycle apart. Once both X and A are in the PE at x0, y0, and the overlay is in the right context, the first add is executed. The second add has a dependency on the first, which uses one of the x0, y0's 2 output ports, one for each of the 2 contexts, to re-enter the PE. Then the output of the second add goes to the multiply PE at x1, y1. Once the second multiply is executed, its value travels to x1, y0. Note that this data doesn't move in a single cycle. All routers and PE outputs are highly pipelined. This all repeats every II cycles, every 2 cycles in this case. We implemented the overlay on Xilinx Alveo U280 with Vivado 2020.1. We used the compiler output, including the static schedule, to generate overlay parameters, such as channel count, the number of contexts, and the PE configurations. On the right is a close-up view of a 3x3 array, and here it is compared to the 19x69 device view. We floor planned the design to optimize Fmax when using the whole chip. Every logic block was assigned to a P block, a physical block, which was set to 10 x 10 to prevent spillage between superlogic regions as we unroll the array over the chip. Another aspect of our careful floor planning was determining the right amount of pipelining, both in PEs and in routers, for high-frequency operation. Between SLRs, we mapped the registers there to Laguna registers and super long lines. We implemented 3 chip-scale overlay configurations of size 19 by 69 and one 4x4 single-channel, single-input PE configuration to compare to other CGRA overlays. We tested each configuration with anywhere from 10 to 100% of PEs as multipliers, rather than soft logic adders or I/O. And as you can see, lower channel count is more desirable for higher Fmax. The goal for these benchmarks is to map them onto an overlay configuration with as few channels as possible. The vast majority of these benchmarks map to 2 or 3 channels once they go through our compiler flow. Comparing to previous work in the CGRA space, Address and HighCube are 2 architectures that have both been implemented as FPGA overlays. Apart from a larger array size, our architecture can scale with a high degree of resource sharing, and our compiler can deal with larger dataflow graphs. We reach higher Fmax than either Address or HighCube on UltraScale Plus. Comparing the 4x4 Mocarabe array to similarly sized overlay implementations, we get anywhere from 2.1 to 2.4 times speedup compared to Address on UltraScale Plus, and 2.6 to 3 times speedup compared to HighCube on the same architecture. Our methodology for comparing to Vivado HLS was to run the compiler for each of our benchmarks for every II from 1 to 5. Then we enroll our single kernel array to every block available in the device, and then give Vivado HLS the same benchmark, II, unroll factor, and target frequency. In the single context case, where every resource repeats the same action every cycle, the gap between Vivado HLS and our work is relatively small. As the number of contexts increases, so too does the gap. When trying to share resources over many contexts, every benchmark has a noticeable difference. In terms of resource usage, Vivado HLS and Mocarabe have similar DSP usage, but Mocarabe does come with a LUT area overhead. If we constrain HLS to the same operator count as Mocarabe and compare target II to achieved II, HLS has no trouble in the single context case. Keep in mind that Mocarabe meets its target in every benchmark. As the number of contexts grow, so does the gap between the target and the actual achieved II. At I equals 5, the gap is very significant for some benchmarks. To conclude, Mocarabe is a fast, flexible FPGA overlay architecture with a custom compiler and a carefully floor-planned implementation on Alveo U280. We have 1.8 to 3.4 times higher Fmax compared to similar overlays on the same FPGA architecture. We have a chip scale array size, and we can perform up to 9.2 times faster than Vivado HLS. Thank you. Our code is available at this link.